welcome back to our channel. This is Science Lectures 256. Don't forget to like, subscribe, and follow us on our social media handles on WhatsApp and on X. And those ones that have subscribed, please thank you so much. We're seeing the comments, and yeah, we prove and pledge to provide better. So as we discussed earlier within our series of biostatistics, we are still continuing with them after the long introduction. Now we are going to look at the specific tests, and we are going to begin with parametric tests, and the first one is a t-test. As you introduced to earlier, t-tests or parametric tests are used to compare means, and you can only compare means ranging from 2 and above. So whenever you have two means, one of the tests that you can use to compare is a t-test, and a t-test is utilized when the value of n is less than 30. When n is less than 30 and you are comparing two means, that is when you use a t-test. Just like any other parametric test, it also assumes that we have homogeneity or variances, unity of variances. Data is normally distributed. So what do I mean by data being normally distributed? Data having a bell-shaped curve. Yeah, those are the assumptions of a t-test. And as I said earlier, it is used to compare two means, specifically two means, and when the value, it is used to compare two means when the value of n is a total number of samples is less than 30. Yeah, and a t-test can be further divided into two. We have what they call a one sample t-test, a one sample t-test, and a two sample t-test. Then the two sample t-test can also further be divided into two. That is a t-test for independent samples, a t-test for independent samples, and a t-test for paired samples. T-test for paired samples. So we say the t-test can further be broken down into two: a one sample t-test and a two sample t-test. So what is a one sample t-test? A one sample t-test is where you assess, it is the one used to assess the likelihood of an individual to belong to a specific group. So in a one sample t-test, we assess the likelihood or the chance of an individual to belong to a specific group, but the value of n in that group is supposed to be less than 30. So whenever you try to compare an individual to a value from a specific group when n is less than 30, that is what we call a one sample t-test, and we're going to see some examples where that is utilized. Then, if it is not a one sample t-test, because in a one sample, as you hear one sample, it is an individual being compared to a group, But we say the t-test can be used to compare means. So when you are comparing two means from different groups, that is a two sample t-test. And the two sample t-test can be for independent samples or for paired samples. And the t-test for independent sample is used to assess or compare the difference between means collected from two different groups. groups. So whenever you are comparing the difference between two means collected from two different groups, between means collected from two different groups, that is a t-test for independent samples. For example, if I collect fish from Lake Victoria, and I collect fish from Lake Choga, and I collect fish, then I sum them, let's say I get their weight, because their weight gives a normal distribution, and I add their weight to obtain, let's say, mean A and mean B. So if I love to see whether their means are the same or different, I would use a t-test. But that t-test is for independent samples, because the fish in Lake Victoria have no relationship or have nothing that joins them to the fish in Lake Choga. However, you can run an experiment, or you can collect data from an individual, and from this individual you collect two sets of data, and you'll have to check whether there is a difference within that data. So whenever you collect data from an individual, and you'll have to assess whether there is a difference between the means obtained from the two sets of data, that is when you use a t-test for paired samples, or sometimes what they call a t-test for matched samples. For example, if you are a chicken farmer and you decide to use black flies as a source of protein, so you feed your chicks in the morning and in the afternoon, and whenever they finish feeding, you take their weight measurements. Realize that you have one chick, and from that one chick you get data in the morning and you get data in the evening. So what you get is the mean of their body weight in the morning and in the evening. So if you love to see whether there is a difference within let's say their growth rate, where there is a difference between their growth rate in the morning and in the evening. So if you love to see maybe whether black flies would provide an alternative protein source, definitely as a statistician or as a biologist, you would have to run a statistical test, and that would be a t-test. But since this data is collected from one individual at different time intervals, use a t-test for matched or paired samples. Yeah, so I would love us now to start looking at specific examples. Very important to note, in this video we are going to combine concepts of what was studied in the introduction alongside the knowledge of visualizing a curriculum later. So if you've not watched those two videos, please do so. The link is just in the description box below. So I want us to look at specific examples of how these two tests would draw the dichotomy. So I have an example here. It says, show whether a fish of length, actually we are looking at now a one sample t-test. I hope I didn't like that. Yeah. So show whether a fish of length 41.5 centimeters was obtained from a pond of 27 fish whose mean length is 45.5 centimeters and standard deviation of 1.5 centimeters. So before you work out any question, you're supposed to look at the different integrities. For example, here they are telling me to show whether a fish, so that would just say that yes, it is one individual. They have talked of a pond. A pond definitely has a lot of fish, but they have given me the mean length. So I am comparing one individual with the mean of other fish, but that fish is, the value of their n is 27, which is below 30. Yeah. So definitely from that you are supposed to know that they have told me to use a t-test, but a one sample t-test, because it is one fish being compared with the mean of other 27 fish. And it is a one sample t-test because the value of n is less than 30. So how would you attack such a question? As you told earlier, any test is run or is carried out to confirm a hypothesis. And as biologists, we shall run our tests to ascertain, to confirm or to prove whether that our null hypothesis is either right or wrong. So the first thing you're supposed to do is to state the null hypothesis that a fish of length 27, of length 41.5 centimeters was obtained from the same pond of 27 fish. And very important here, if I forget, we should state our null hypothesis by writing H of. So our null hypothesis, what you're supposed to first write before you run any test. Even when you're doing research, the first thing you're supposed to always formulate or write is the null hypothesis, because it is the reason why you run the test. So our null hypothesis is a fish of length 41.5 centimeters was obtained from the same pond of 27 fish. After that, that is our null hypothesis. Then, since this is a one sample t-test, you're supposed to know the formula. T is equal to mean, the variable, which is the length in this case, minus the mean of this population that you are comparing with, divide by standard deviation. This is the formula that you're supposed to carry in your head, that whenever I'm dealing with a t-test, for a one sample t-test, it is the value that have been given minus the mean divided by the standard deviation. So if I'm to substitute in my formula, I get 41.5 centimeters, which is not necessary in this case, minus 45.5 centimeters, which is not necessary in this case, divided by 1.5. So I'll utilize our calculator to do some simple math. Minus 45.5 divided by 1.5. I get my t as negative 2.67. However, all the tests that we shall discuss in our lectures would be two-tailed tests. What do I mean by a two-tailed test? If this is my distribution curve, it has two extremities, a negative side and a positive side. So I have negative 2.67 as my calculated value, which we will denote as T curl. T curl is equal to negative 2.67. Then we have what they call statistical tables. Within the description box below, we have a link that will take you to the statistical tables that we are going to be utilizing in this class. However, if you are unable to attain them, one of the books that I would recommend you to use is Field Statistics for Biologists. That is a very good book, and it's one of the books that we utilize in this class. Still, you will obtain the same tables. So what you do after obtaining the calculated value, which is T curl, you go to your statistical tables. I don't have tables here in the hard copy, so I have them in my soft copy, and from these tables that I have here, I obtain my calculated value. My calculated value is 2.056. But however, we say this is a two-tailed test. It can be a positive or it can be a negative. So the calculated value that you obtained is a negative. My t-tab is negative 2.056. But how did I get here? So when you look at those tables in those books that I have recommended, or the ones that you'll access in the description box below, you look for appendix number 2, and we are specifically using the distribution table, distribution table. So how does that table look like? Let me just draw a rough estimate. We have a one-tailed above, we have two-tailed below, and saying in this class we shall be using a two-tailed. Then on this side, on the vertical scale, we have the degree of freedom. So for a one-tailed test, the degree of freedom is equal to n minus 1. Degree of freedom is equal to n minus 1. So I have 27. I subtract 1, I get 26. So when you come to these tables, you look for 26. 26 is around somewhere here. Then there is, as you told earlier, there is what we call confidence interval. Our confidence interval can be at 95% or at 99%. However, in those statistical tables, we don't have 95, we don't have 99. But you have, instead you have 0.05 and 0.01. How did we get here? 100 minus 95, you get 0.05. Then 100 minus, you get 5, then 5, when you turn it back into, you make it a fraction, or you bring it back into terms of 100, you get 0.05. Then 100 minus 99, you get 1. The same thing, then that's how you get 0.01. So, in this case, my critical value was read off at 0.05. So, that column where 0.05 and 26 meet is where we read off our things. Or another person can decide to use 0.01. Still the same thing, where 26 and 0.01 meet is where we read off our critical value. That is how we obtain our critical value, which is in this case T tab. Very important to note. Before you go to the tables, you obtain the degrees of freedom, which is n minus 1, which is in this case we had 27 as our n. We subtract 1, we get 26, and I decided to read it off at 0.05, which is our confidence interval. So in this case, the value that I got where 0.05 and 26 meet was 2.056, and since this is a two-tailed test, it can be a positive or it can be a negative. Another person can decide to use 0.01. Still, they will obtain a different value, and that can also be considered. So, what happens when you have the calculated value and the tabulated value? You can see that our calculated value is greater than our tabulated value. One other thing that I forgot to tell you was the decision rule. A decision rule is what you base on whenever you are running a statistical test to either reject or accept the null hypothesis. For a t-test, the decision rule is very simple. Whenever our calculated value is less than our tabulated value, you accept the null hypothesis. However, whenever our calculated value is greater than our tabulated value, you reject the null hypothesis. Take the null hypothesis. How does this come about? If I try to represent the same thing graphically, if this is my distribution curve, and I try to say this is at 95, which is 0.05, then 0.05. Anything within here makes you accept the null. Anything below the critical value makes you reject the null. So whenever you reach here and you don't know that accept the null or reject, you just draw this curve and you see where does the figure fall. In this case, for example, if I am to look at this was within this here, t tab is equal to 2.057, which is negative. So when I come and draw my curve here, so my critical value, I try to off at 95% is negative 2.057, but it can be 2.057, it can also be a positive. I have negative 2.67, which lies between here. And we said anything outside this curve you reject. So I have somewhere around here 2.67. So I reject. But as biologists or as scientists, we don't stop there. We are supposed to make conclusions, whether to accept or reject our null hypothesis. So what you do, you come back and tell the one who said the question, or you come back and explain to whoever is going to the results that it is unlikely that a fish of 41.5 centimeters came from the same pond of 27 fish whose mean length is 45.5 centimeters and standard deviation is of 1.5 centimeters. You don't stop there. You also include two more important things. You include the calculated value, the t value which you've calculated, which is, in this case it was negative 2.67. Then you include the probability. Whenever you reject the null, that means the probability is less than the critical value. Whenever you accept the null, the probability is greater than the critical value. And the other thing, you specify the test you've used. It is a one sample t test, a one sample t test. So just to run back through whatever we discussed, you state the null hypothesis, then you come state the formula, substitute it in the formula, obtain the calculated value, which is t cal. Then from there, you go to the t distribution table, specifically appendix 2, obtain the critical value at specific confidence intervals. It can be 0.05, it can be 0.01. And we say this is a two-tailed test. It can be positive or it can be negative. After that, compare and see. So long as the value lies within this, or it is less than the critical value or the tabulated value, accept the null. Whenever it's greater than the critical value or the tabulated value, you reject the null. Then you come and conclude. However, this is just a tip. You can clearly see that this fish has a very big length, which is almost close to the average of the other 27 fish. This could specifically tell that yes, the fish can come from the same pond. But as scientists, we just don't base on hearsays and observation to draw conclusions. We draw them using facts, and that's why we do these tests. We are still continuing. I want us to do another example of a one sample t test. So a sample of common bulbuls measuring 14, 16, 15, 16, 17, 16, 15, 16, 15, 18, 18, 19, and 20 was obtained if another common bulbul measuring 25.5 centimeters was obtained in the museum. Show at 99% whether it came from the same sample. We said one of the first things you consider is the value of n. So how do I get my n? I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So my n is 14. So, and I'm trying to compare one bulbul to many other bulbuls. So what would you do in such a question? You first obtain the mean, then you obtain the standard deviation from your calculator. If I have to do my math chaps. 14, 16, 15, 15, 16, 17, 17, 16, 15, 18, 18, 19, 20. Yeah. And we are applying aspects of utilizing a calculator. As I said earlier, we are trying to employ the various aspects of utilizing a calculator. So for those of you that don't know what I'm pressing, there is a video that we recorded of how to use a calculator to get both mean and standard deviation. So from my calculator, my mean is 16.42. I press shift 2 again, then my standard deviation is 1.74. I repeat, if you don't know how we've done those two, please check there is a video teaching how to use a calculator to obtain both mean and standard deviation. So you can see my n is 14. I have the mean, I have the standard deviation. So I come and state my null hypothesis that a common bulbul of 25.5 centimeters came from the same sample. So I come and say my t is equal to my value minus the mean divided by the standard deviation. T is equal to 5.5 minus 16.42 divided by 1.74. Simple math. 25.5 minus 16.42 divided by 1.74. I get my t calculated as 5.22, because it's 5.218. When I round off, I get 5.22. So we said you go to your tables, and they are specified at 99%. We said at 99% of the tables is represented as 0.01. So I obtain my tabulated value or my critical value when I check my tables here. My critical value is 2.17. 2.17. So sorry, I forgot to talk about the degree of freedom. We say it is n minus 1, which is 14 minus 1, which gives me 13. So you look for where 13 and 0.01 meet. What they do? Meet is the value that you read off. So this is my calculated value, my tabulated value, and this is my calculated value. So you can see if I draw my distribution curve, my critical value is 2.17, but I'm having, this is the negative, then I have 2.17. I'm having 5.22. So we say anything within this region you accept, anything outside this region you reject. Or if you don't want to go through this, we say whenever our calculated value is greater than our tabulated value, you reject the null hypothesis. I have 5.22 greater than 2.17. Therefore, I reject my null hypothesis. I come back and I conclude it is unlikely that a common bulbul, I can extend it from here, it is unlikely that a common bulbul of 25.5 centimeters came from the same sample of 14 bulbs of, I state the mean 16.42, standard deviation of 1.74, and I state my t calculated, which is 5.22. We said whenever I reject the null That means your probability is less than the critical value. The probability is less than the critical value, and we said the test uses a one sample t test, one sample t test, one sample t test. So throughout this video, we've discussed what a t-test is, the various types of t-tests, and done some two examples or showing you how one sample t-test questions are set. Very important to note, you look at the value of n, because you can have a similar question where n is above 30. We shall see what you do in that case. Look at get the mean, get the standard deviation if given, then you substitute in this formula, substitute it in this formula, which is very important. After that, you obtain the t calculated value. Go to your t distribution tables, which is appendix 2, obtain the tabulated value, or what they call the critical value. Compare the calculated value and the tabulated value. Whenever the calculated value is greater than the tabulated value, reject the null. Whenever the calculated